So, good evening. We will consider this throughput networks. We will continue our study of throughput networks, and also we will consider time permanence theorem, and we will be solving the previous year assignment 11 for this network analysis course. So, this network analysis course is being run by NPTEL, and it was taught by Professor Tapas Kumar Bhattacharya in the Department of Electrical Engineering, IIT Kharagpur. So this course is being rerun, and so we are conducting problem solving doubt-clearing sessions over here. So whatever doubts you have, you can ask in this session. And we were studying throughput networks in the last week, and we solved the various sums of the throughput network. And we will continue our study further. So let us begin. Study a throughput network. We have already studied. We will just do some further analysis of throughput network and get some further results which we can use while solving our science, and we can get further insight into the use of throughput networks. So let us consider this is a throughput network, right? So this is the voltage plus minus V1 at the input terminal of the network, and the current I1 is flowing into the network. Similarly, at the output port, current I2 anyway will flow into the network, and the polarity of the voltage is given like this. Okay. So there are various parameters which we can use. There is known as we studied. This is like a sort of recap. We consider Z parameters. The Z parameter of the network. These are basically the impedance parameters of the network, and then we found using open circuit tests, we find the Z parameters. Similarly, we study Y parameters of the network, or these are known as the admittance parameters for the network. And these parameters are determined by conducting short circuit tests for the throughput network. Similarly, we also consider ABCD parameters. ABCD parameters. We studied ABCD parameters. And this ABCD parameters is very useful in power systems where they are considering the sending end of power and the receiving end of power and the transmission line. They characterize it using ABCD parameters, and there's a very complex, there's a sort of derivation where you characterize the ABCD parameters in terms of the characteristic impedance of the transmission line and various other factors they consider, and they determine the ABCD parameters of the transmission line. So this is a very useful ABCD parameter, and when we are cascading to networks, and representing the network using ABCD parameters will help us in finding the equivalent ABCD parameters of the network, of the equivalent network. So we will do that in this session also. Similarly, we consider what is known as hybrid parameters or edge parameters. So this set of hybrid parameters or edge parameters is very useful for the small signal modeling of DTT. This comes into the picture, right? So we also consider various other factors like when it's a network symmetrical. When do we have a symmetrical network? Plus, we also consider when we have a reciprocal network. When it's a network reciprocal and when it's a network symmetric, and based on the ABCD parameters, we are determining that. So let us continue further study. So we have seen the results for when it's network is symmetrical, when it's network reciprocal, but let us try to retrieve them. Let us consider a two-port network, which is written in terms of the ABCD parameters. And we will try to determine what conditions has to be satisfied such that the network is reciprocal and such that the network is symmetrical. Okay? So the, let us consider this network and we are representing it using ABCD parameters. And we will try to find the equations, you try to find the relation required between the ABCD parameters and that is symmetrical reciprocal. So we know the ABCD parameters are written as V1 is equal to A into V2 plus B into I2 A1 is equal to C into V2 plus B into I2. This said, like these two equations, we can represent in matrix format as follows. V1 I1 is equal to A B C D and V2 I2. So the input parameters are related to output parameters. Okay, there's one thing over here, which is actually is minus I2. Because when we consider a two-port network, we want to see the current flowing out for the ABCD. In the case of ABCD parameters, like the current is coming out of the circuit. And this will come in terms like this. A into V2 minus B into I2 and I1 is equal to C into V2 minus D into I2. That is represented in terms like this. V1 upon I1 is equal to A B C D to V2 to minus I2. So this is the relation for the two-port network. So when do we consider the network is symmetric? When we consider the network is symmetric. Okay. For the network to be symmetric, what we will do is we will apply voltage as V1 here and we will current which is entering in, and we will consider the output to be open circuit. Okay, we will consider the output to be open circuit. So if that is the case, that means I2 is equal to 0. Okay, this means I2 is equal to 0. So what we will obtain is V1 is equal to A into V2 minus B into 0. So we get V1 is equal to A into V. Similarly, we get I1 is equal to C into V2 minus D into 0. So effectively we get the input, that is I1 upon V1 is equal to C upon A, right? So this is the, so here I1 is the response. Okay, I1 is the response, and this is the input, which is applied at the one terminal. Okay, and we have kept a condition when we are trying to determine the parameters that the output terminal is open circuited, that is port 2 is open circuited, so current I2 is equal to 0. Now we will consider a similar condition in which we are applying a voltage source to the second port, and we will measure the current which flows into the network, and also we will consider that the input, that port 1 now is open circuit. It's just the opposite condition we are applying because we want to know what condition is required so that the network is symmetric. So what we will do is, this is the same two-port network. We apply voltage source here, plus minus V2. This is the response, which is actually equal to minus into I2, because we actually consider the current to be in the outward direction. And this is open circuited, so that means current I1 is equal to 0. So when we apply this condition to this network, what we will get is V1 is equal to A into V2 minus V into I. Okay, in this there is no change. Then we get I1, we know I1 is equal to C into V2 minus D into I2. Okay, so but we know I1 is equal to 0. We know I1 is equal to 0. That would mean that C into V2 minus D into I2 will be equal to 0. Or CV2 is equal to D into I2. This would mean that I2 upon V2 is equal to C upon D. Now this is the response. I2 current is the response, V2 is the input, and if we want our network to be symmetric, okay, we want our network to be symmetric, then what will be the case is I1 upon V1 should be equal to I2 upon V2. That would mean C upon A should be equal to C upon D. From this we get that the result is A is equal to D. So if we want to know that our network is symmetrical, and if the network is represented in terms of two-port network, in terms of ABCD parameters, then if A is equal to D, then we can say that the network is symmetrical. Okay. So one more point which you should note down is the dimensions. See, V1 is equal to A into V2 minus B into I2. So effectively, A is a dimensionless quantity because A is the ratio of V1 upon V2. Okay, it's a dimensionless quantity. Here, if you consider B is in terms of impedance, B is in terms of impedance because impedance into current is voltage. So this is voltage. This also B has to is in dimension of impedance. So impedance into current is voltage. So this also should be voltage. So that means A is dimensionless. Similarly, this is current. If this has to be current, C should be in terms of admittance. Okay, and D should be dimensionless. So that means we get A equal to D, and that also is dimensionally correct because A is dimensionless, B is dimensionless. So this is another way of verifying that what condition we have obtained, whether there is any sort of error in the condition, whether we made any calculation mistake or anything. Okay, so this is for finding out if the network is symmetric. So we will consider the definition which was provided by Professor Tapas Kumar Bhattacharya. Okay. So in a symmetric two-port network, input and output ports can be interchanged without changing the voltage and current in the port. Now, so what does this mean is there's no distinction can be made when port 1 is made as an input and port 2 is made an output port. Similarly, when port 2 is made an input port and port 1 is made an output port. So what? So any port can be the input port or output port, and it doesn't make any difference according to that. Then this will be possible if the driving point admittance or admittance looking from port 1 and port 2 are equal. So the driving point at the input, when we apply voltage and the current, what impedance is seen by the network at that point, that is known as the driving point impedance or the admittance. And admittance is the reciprocal of that impedance. So if that driving point impedance or admittance is equal from the port 1 or port 2, then we say the network is symmetric. And if this ABCD parameters are also known as T parameters, and so if the network is modeled with T parameters, then for it to be symmetric, the condition is that A should be equal to D, and this condition we also have proved it. Okay, so when we have solved this set of equation, we have determined a driving point impedance. That is, we have determined a driving point admittance. The I1 upon V1, this in terms of admittance. Similarly, I2 upon V2, also is in terms of admittance. So we have determined the driving point admittance, and then we have found out the relation A equal to D. Okay. We will consider now we try to consider a case or to determine what will be the condition of the network is for the network to be reciprocal. Okay. So we will consider the same network. This is the same ABCD parameters. ABCD parameters. And the same relation we have. That is V1 is equal to A into V2 minus A into I2. And I1 is equal to C into V2 minus B into I2. And now we want to see the condition that let me just write it down. So I apply a voltage source at the port 1, okay, of V1. This is my two-port network. Then I short the output, and this is my current I2. Okay. This is my current I2. So now we want to see what would be. So this is the input. So V1 is known as the input, and I2 is the response. Okay. So we will try to find, and here V2 is B equal to 0 because it is short. So when we apply this condition, what we get is V1 is equal to minus V into I2. So this I2 for V1 is equal to minus. So I2 upon V1 is equal to minus V. So this is the this is the ratio of the response to the input. Now we will consider it in the opposite direction. That is, we apply the input to the port 2. We will short circuit port 1. And so that would mean V1 is equal to 0. And this is current I1 which is flowing. Okay. When this is the case, what will happen is V1 is equal to 0. So we know V1 is equal to A into V2 minus B into I2. So if this is 0, so 0 is equal to A into V2 minus B into I2. So we get B2 is equal to B by 2 from A. Okay, so this is the relation we have got for V2 in terms of I2. Similarly, when we apply the condition that V1 is equal to 0, now we know that I1 is equal to C into V2 minus D into I2. And we want it in terms of I1 and V2. So in this equation, V2 is equal to B upon A I2. We will further write it as I2 is equal to A into V2 on B. And we will substitute this I2 in this equation. Okay. So we get I1 is equal to C into V2 minus D into I2. I2 is A into V2 upon B. So D to A, V2 on B. So we get I1 is equal to B into C V2 minus A into D V2 on B. So we get I1 on V2 is equal to BC minus AD on B into V2. Okay, into V2. But we have neglected the fact that in this network, when we apply the input over here, the current was in the outward direction. But when we applied it over here, the current was in the inward direction. Then we need the opposite. So that's why we will write that is minus I1 on V2 is equal to AD minus BC on B into V2. Now we will compare so this is the required output, or that is the response, and this is the input. So we will, when we compare, okay, this V2 must go. Okay. Now when we will compare these two, what we will get is I2 upon V1 is equal to minus D. And we have made a mistake here. I2 upon V1 is equal to minus 1 upon V. Okay. So now we will compare I1 upon V2 is equal to I2 upon V1. That we get it to be minus of AD minus BC upon B. This is equal to minus 1 upon B. So we get it to be AD minus BC is equal to 1. So thus we have obtained the relation when the network is reciprocal, when a T network is reciprocal. Thus the two-port network is to be reciprocal, then I2 upon V1 is equal to I1 upon V2. So minus 1 upon B should be equal to BC minus AD upon B. So we have also got that this is AD minus BC. Now if we will consider the determinant of the two-port network, or the just represent in terms of ABCD parameters, ABCD parameters. And this is a matrix T. It is given by A, B, C, D. So the determinants of this matrix T is equal to A into D minus B into C. And if we want this network to be reciprocal, then the condition we have obtained is AD minus BC is equal to 1 That would mean that the determinant of the matrix must be equal to 1. So if this is the case, then we consider that the network is reciprocal. If this is a reciprocal network, we will consider. So that's we have proved we have determined the relation for whether a network is symmetrical or whether a network is reciprocal via ABCD parameter for network which is represented in terms of ABCD parameters. In a similar manner, you can do it for a network in case it is represented in Z parameters or it is represented in terms of Y parameters, or if it is represented in terms of H parameters. So it will still be the same. Okay. So now we will proceed further. So in the lectures which Professor Tapasmo Bhattacharya has been teaching in week 11, he has considered the case for reciprocity, how Z12 should be equal for considering Z parameters. Okay. He has considered a case where for reciprocity, we have Z12 should be equal to Z21, and if it is to be symmetric, we need Z11 should be equal to Z22. And how they have determined that, how he has determined it for it in terms of and for Y parameters also he has considered the case for symmetricity as well as for reciprocity. Similarly, they have determined it for H parameters also, for symmetricity and for reciprocity. And for ABCD parameters also, they have determined it, like how we have also done. Okay. This is for network to be symmetric. Now we will consider a case for a series connection of two-port networks. So in case we have a series connection of two-port networks, how will be represented? Okay. Which parameters to use in case it is series connected, in case it is parallelly connected, or in case it was connected in cascade, then which set of network, which way to be practiced to represent the networks. We consider the series connection of two-port networks. So we have a network which is given network 1. Similarly, which is network 2. Okay. This is how it is series connected. So this is V1, which is applying. This is applying to I1. And this is V1 prime. And this is also V1 double prime. The V1 prime is applied to network 1, V1 double prime is applied to network 2. Current which is flowing into network 1, I1 prime is equal to I1. And it comes out like this, and it also goes again like this. This is same current I1. Similarly, this is the current I2 which is flowing into the network 1 without second port, and it will be flowing out as well. I2. Then it goes into the input of network 2, and it flows out. And this is the voltage V2 which is applied effectively. And this is plus minus V2 prime, and this is plus minus V2 prime. Okay. So this actually is I2, and this is I2 prime which is flowing into the network, and this is I2 double prime. This is I1 double prime which is flowing into the network 2. So what we know is, what we can say is I1 prime is equal to I1 double prime, which is equal to current I1. Okay, which is similarly this voltage V1. This V1 voltage is the sum of this voltage V1 prime and V1 double prime. So V1 is equal to V1 prime plus V1 double prime. Similarly, for the second port, for the output port, I2 prime is equal to I2 double prime, which is equal to I2. Similarly, V2 is equal to the sum of these voltages V2 prime and V2 double prime. V2 is equal to V2 prime plus V2 double prime. Okay. So now we can and we represent and now we will understand why when the networks are connected in series connection, why it is best to represent in terms of Z parameters. Why using Z parameters in such a case is useful to simplify our analysis. So let us consider networks to be represented in terms of Z parameters. So we have V1, V2, V1 prime, V2 prime is equal to Z11 into Z1, Z12 prime, Z21 prime, Z22 prime is into I1 prime and I2 prime. Okay. Since I1 prime and I1 prime is equal to I1 and I2 prime is equal to I2, we can write it down as Z11 prime to Z12 prime to Z21 prime to Z22 prime into I1 into I. So this is for 1. Now we will consider for network 2. For network 2, that is represented as V1 double prime and V2 double prime is equal to Z11 double prime, Z12 double prime, Z21 double prime, and Z22 double prime into I1 double prime, I2 double prime. Okay, this is equal to Z11 double prime, Z12 double prime into Z21 double prime into Z22 double prime into I1 into I2. Okay, this is the case. So that's why the Z parameters of network 1 and the Z parameters of network 2 we have represented using these matrix equations. Now we will try to find the simplified for the overall Z parameters for the overall network, which consists of two-port networks in series connection. So the overall network should be represented as V1 and V2, that is the total input voltage at port 1 and the total voltage at port 2 for the effective network. V1 and V2 should be equal to from Z11, some Z12, Z21, and Z22. Here it will be I1 and I2. And here it will be I1 and I2. This is the effective voltage, effective way of representing the entire two-port network. Now we know that V1 is equal to V1 prime plus V1 double prime. Similarly, V2 is equal to V2 prime plus V2 double prime. Okay. So we can write it as V1, V2 is equal to V1 prime, V2 prime plus V1 double prime and V2 double prime. So we can write it as V1, V2 is equal to Z11 prime, Z12 prime, Z21 prime, Z22 prime into I1 into I2 plus Z11 double prime, Z12 double prime, Z21 double prime, Z22 double prime into I1 into I2. Since I1 and I2 are common, so we can write it effectively as V1, V2 is equal to, and so this, the first element or the first row, like the element of the first row and first column and the element of the first row and first column of the other matrix, they are either. So it becomes Z11 prime plus Z11 double prime. Similarly, the second element of the second row and the second element of the second row for the other matrix, they are also added. So it becomes Z12 prime plus Z12 double prime. Similarly, over here it becomes Z21 prime plus Z21 double prime. And here it becomes Z22 prime plus Z22 double prime into I1 into I2. So, thus, when we compare equations A, equation B for the overall network, we get Z11 is equal to Z11 plus Z12 double prime. Z12 is Z12 prime plus Z12 double prime. Z21 is equal to Z21 prime plus Z21 double prime. Z22 is Z21 prime plus Z22 double prime. Or matrix format is Z11, Z12, Z21, Z22. So that's Z1, Z21 prime, Z21 double prime, Z12 prime, Z22 prime plus Z22 double prime. Okay. So thus we have found the condition for the Z parameters. So they are connected in series. So then we use Z parameters, and Z parameters are very useful to find the overall parameters so that we put network. Okay. Now we consider when there's a cascade connection of two port networks. Where input V1 is applied, and here I1 is the current. This is the output V2, and this is the current I2 which is flowing out. So this intermediate location, we will consider it to be Vx, this current to be I. Okay. This we consider to be the case. So we know for ABCD parameters of network 1, we have P1, A1 is equal to A, B, C into D, Bx, and Dx. This is, we don't need to input negative sign because this current Ix is in the outward direction. Okay. If it was in the inward direction, if it was suppose like this, then we would have to put a negative sign. But since it is already in the outward direction based on the convention for ABCD expenses, we write it as V1 into I1 is equal to A BX plus B into IX. Okay, I1 is equal to C into BX plus D into IX. So this is the matrix representation for network 1 of the input and output relation. Now for the network 2, Vx is the input voltage and Ix is the current which is entering the network 2. And V2 is the output voltage and I2 is the output current and I2 is the output tension. So again, we don't need to sign. So for ABCD parameters on network 2, we have it as Vx, Vx. This should be A1, B1, C1, D1 because they represent the ABCD parameters on network 1. So here Vx and Ix is equal to A2, B2, C2, D2 into V2 into I2. Okay? Because Vx, Ix is the input for network 2 and V2, I2 is the output of network 2. So they are represented in terms of ABCD parameters of network 2 as Vx, Ix is equal to A2, B2, C2, D2 into V2 into I2. So this is the two equations we have. So let us name this as equation 1 and this is as equation 2. Okay. Now we want to find the overall ABCD parameters, which should be given as P1 into I1 should be equal to A, B, C, B, and here it should be B2, I2. Because this is the overall output and this is the overall input. Okay. So now what do we do is we already know P1 upon I1 is equal to A1, B1, C1, B1 into Vx and Ix. This is from 1. Okay. Now we substitute two in 1 and we get this is 2. 2 is Vx in terms of V2 I2. Vx we write it down as V1 I1 is equal to A1 B1 C1 D1 Vx will address A2 B2 C2 B2 into V2 into I2. This is our overall equation. So now what we get is the overall ABCD parameters A, B, C, D is equal to A1, B1, C1, D1 into A2, B2, C2, D2. So this is the overall ABCD parameters in terms of the equivalent ABCD parameters of network 1 and network 2. And this is for a cascade condition. Okay. So we just have to multiply this matrix with this matrix and we will get the overall ABCD parameters of the network or overall T parameters. Of the network. Okay, we will consider an ideal transformer. There is considered turns ratios here. It is number of turns for secondary upon number of turns of primary is equal to A upon 1. We know the relation that B2 will then be equal to A into B1 and I1 will be equal to A into I2. Okay, so this is the relation we have. This is the relation for an ideal point where we don't consider any losses like in case of a real transformer, there is something known as the proper loss. That is the losses which occur due to the windings. In the windings of the transformer, the resistance of the windings. So when current flows through it, there is a loss. Similarly, there is something known as a leakage flux. Leakage flux also is there. So this, when these factors increase, the transformer deviates from the actual ideal transformer. So when you consider ideal transformer, we are ignoring all these factors. This is just basically a simple representation for gaining, an overall understanding of your transformer. And when we further study it for higher applications, then you will get a more deeper and in-depth and accurate understanding of the equivalent circuit of a transformer. So this is just a rough one. So in the actual equivalent circuit, there's a copper loss component, there is a leakage flux component. Similarly, there's a component which represents the core loss. There's a resistance which represents the core loss, and there is an inductance. This one is a magnetizing inductance. Which represents the which represents how much magnetizing current is in the total direction. So all these things are there which we are ignoring in our simplified analysis. So what we have found is we have two equations. We have V2 is equal to L into V1 and I1 is equal to A into V2. Okay, these two equations we have. Now let us assume we want to represent it in terms of ABCD parameters. We want to represent this circuit in terms of ABCD parameters. So what do we know? For ABCD parameters, we have V1, I1 is equal to A, B, C, D, V2, and minus I2. So they have considered convention that they have considered without convention. So we know that there are two dots which represent the polarity of the voltage in which when we have studied also the dot concept when there is a coupling. So basically there's a coupling between the input side and the secondary side. So if the current is flowing into one terminal, then the current has to flow out of the dot terminal. So in case of the primary side or the input side one, the current I1 is flowing into the dot, and so the current the secondary side will flow out to the dot. That's why I2 is shown for out. When this is the scenario, we can get V1 I1 is equal to V2 CD V2 plus I2 because I2 is flowing out to the negative. So what do we write this as? V1 here we written as V2 upon A and I1 is equal to A into A2. So then we can represent this in terms of ABCD parameters and V1 into an I1 is equal to 1 by A 0 A 1 into V2 into I. This is equal to 0. V1 I1 is equal to 1 by A 0 A and 0 into V2 into I. Okay. So thus we have found the ABCD parameters. Similarly, there are other parameters also which we can find. This is the T parameters. These are known as the T parameters. These are the T parameters or the ABCD parameters. Similarly, we want to find the H parameters or the hybrid parameters. V1 is equal to H11, V1, H12, V2, and A2 is equal to H21 and A1 plus H22 into V. Then when we compare these equations, V1 is equal to V2 upon A. Similarly, I2 is equal to I1 upon A. We get V1 and I2 is equal to H1 and I1 is 0. H1 to V2 is 1 upon A. Similarly, I2 is, so this also comes out to be 1 upon A. This comes out to be 0. So they have considered A to be n1 upon n2, but they have considered A to be n2 upon n1. And they have also got it in terms of 0 A, A 0. But for us, we consider reciprocal. So we got it in terms of 0, 1 by A, 1 by A, and 0. So what we have assumed here is n2 upon n1 is equal to 8. But what they have assumed in the lecture, n1 upon n2 is equal to 8. This was assumed in the lecture. So just to avoid confusion, what I will do is I will write it in terms of equal to 0 is n1 upon n2, and this also is n1 upon n2, and this is 0. Okay, just to avoid confusion. Because if we write it in terms of this, then it is uniform. For both cases, it will be the same. Okay. So thus we have represented an ideal transformer in terms of ABCD parameters as well as in terms of H parameters, hybrid parameters. Yes, we practice, but this was an ideal transform. When it becomes an actual transformer, then there will be further changes in these things. So over here we made a mistake. Should be I1 is equal to A into I2, so this will be 0 into A. So V1 I1 is equal to 1.8 0 A into V2 by I2. This is for a single transformer. Now let us consider a case when there are two transformers which are connected in cascade. Yeah. One is to A1, one is to A2. This is V1, this is R1. This is Vx, this is Rx. Here again it will be Vx, and this will be V2, and this is output I2. So when we represent this transformer in terms of ABCD parameters, we have these are ideal transformers we keep in mind. V1 upon I1, this comes out to be 1 by A0, 0, A. So this comes out to be 1 upon A1, 0, 0, A1 into Vx and Ix. Okay, because Vx and Ix is the output of the transformer 1. Similarly, for the transformer 2, we have Vx, Ix is equal to 1 upon A2, 0, 0, A2 into V2, A2. Now we want to find the overall transformation between this input of this to the output over here. So we will substitute this we will substitute this Vxix in this equation. We will get V1 I1 will be equal to 1 upon A1 0 0 A1 into 1 upon A2 0 0 A2 into V2 into I2. So we get V1 I1. So when we do the multiplication, what we will get? 1 upon A1 into 1 upon A2, that is 1 upon A1, A2. Then 0 into 0, so just 0. So plus 0 over here. Similarly, 1 upon A1 into 0, that is 0. 0 into A2, that is 0. Similarly, 0 into 1 upon A2, that is 0. A1 into 0, it is 0. Similarly, 0 into 0, this is 0. Plus A1 into A2, this is A1 into A2. So we get V2 I2. Or we can write it as V1 I1 is equal to 1 upon A1 A2 0 0 A1 A2 into V2 A2. So this is how we have got the overall MCD parameters for two ideal transformers when they are connected in series, when they are connected in cascade connection, when it is a cascade connection. Okay, so now we have done a whole lot of theory. We will go and try to solve some example sums which was done in the previous year assignment 11. And we will try to solve them, and we will try to get an understanding of this. So what possible sums which can come to us. So Okay, so we will try to solve the question. We will try to find the current I1 and I2. Okay, so if we will carefully observe this circuit, there are there's a 2-volt network which is given, which has some certain Z parameters are given as follows. And there's a at the input port 1, there is a voltage source applied and plus a resistance in series. Similarly, for the port 2, there is a resistor connected to the output port 2, and it is a fixed resistor. So we know what is the relation between the voltage at output 2 with its current. Since the voltage polarity is plus minus V2 and the current direction is like this, we know if we apply KVL, we have V2 plus 20 into I2 will be equal to 0. Okay, this is the relation for the input port for the output for the port 2, the relation between the voltage and current. So we can write it as V2 is equal to minus 20 into I2. Okay, we write it V2 is equal to minus 20 into I2. So now we know based on the ABCD parameters, we have V1 I1 is equal to 20, 35, 35, 50 into, okay, this is V1 V1 V2 into I1 into I2. So this is the Z parameters. So we get V1 is equal to 20 into I1 plus 35 into I2, and V2 is equal to 35 into I1 plus 50 into I2. Now we know V2 is equal to minus 20 into I2. So we will substitute that in this equation and we will get as follows. Minus 20 into I2 is equal to 35 into I1 plus 50 into I2. Or we get minus 70 into I2 is equal to 35 into I1. And we get I1 is equal to minus 2 into I2. So this is the relation we get, that is I1 is equal to minus 2 into I2. And we will substitute, let me number these equations. This is equation 1, equation 2, equation 3, equation 4. Now I will substitute equation 4 in equation 2. I will get V1 is equal to 20 into I1 plus 35 into minus I1 upon 2. So this will be equal to 40 into I1 minus 35 into I1 upon 2. Or we can get it write it as V1 is equal to 5 into I1 upon 2. So this is equation 5. Now when we apply KVL to this mesh, we will get 20 minus 10 I1 minus V1 is equal to 0. We substitute the value of V1, we get 20 minus 10 I1 minus 5 by 2 I1 is equal to 0. Or we write it as 40 minus 20 I1 minus 5 I1 is equal to 0. So we get 40 is equal to 25 I1. So I1 is equal to 40 upon 25. That is equal to 8 upon 5. that is equal to 1.6 ampere. Okay, we get I1 is equal to 1.6 ampere, which is in the required range for the answers. Similarly, we know that I1 is equal to minus 2 into I2. So I2 is equal to minus I1 upon 2, which is equal to minus 1.6 upon 2, which is equal to minus 0.8 ampere. Okay, so we get I1 is equal to minus 0.8 ampere, and we will check it. No, I2 is equal to minus 0.8 ampere. I2 is equal to minus 0.8 ampere, and when we check the answer, it is in the correct range. Okay, so thus we have solved this question 1. So we will have a break for 2 minutes, and we will return. So we will now be solving this question where we have to find the equivalent and parameters. So this is so what we if we observe this I1 current remains the same to the input port 1 and I2 same current is flowing because they are connected in series. The resistor is connected in series with the output terminal in port 2, with the output terminals of port 2. So we what we desire to obtain is V1 prime, V2 prime is equal to Z1 convert equal matrix Z into A1 into I2. Okay, the Z matrix we will denote later. So now what do we know is we know V1 and V. This is Z outer. Okay. We know V1, V2 is equal to Z inner into I1 into I2. So we have V1, V2 is equal to 50, 80, 60, 70 into I1 into I2. Into I1 into I2. Now we know that V1 prime is equal this when we apply KVL here, we get V1 prime is equal into minus 10 I1 minus V1 minus 20 I1 is equal to 0. So we get V1 prime is equal to V1 plus 30 into I1. Alright? This is equation 1. Similarly, when we apply KVL in this outer loop, we get V2 prime minus 30 into I2 minus V2 prime minus 30 into I2 minus V2 minus 40 I2. And here it will be minus 40 into I2, which is equal to 0. So we get it as V2 prime is equal to V2 plus 70 into I2. This is equation 2. Now we know V1 is equal to 50 into I1 plus 80 into I2 from the matrix. 50 into I1 plus 80 into I2. This is equation 3. So what do? We put equation 3 in equation 1 and we will get V1 prime is equal to 50 into I1 plus 80 into I2 plus 30 into I1. Or we write it as V1 prime is equal to 80 into I1 plus 80 into I2, and this we will write it as equation A. Okay, this is our overall equation A. Now we know from this V2 is equal to 60 into I1 plus 70 into I2. We have V2 equal to 60 into I1 plus 70 into I2. This is 4. So we put 4 in 2 and we get V2 prime. That's right. V2 prime is equal to 60 into I1 plus 70 into I2 plus 70 into I2. So we get V2 prime is equal to 60 into I1 plus 140 into I2. So what do is we write we write equations A and B in terms of matrices and we get V1 prime V2 prime is equal to 80, 80, 60, 140 into I1 and here I2. So this is the Z outer matrix. So this is Z11 outer, this is Z12 outer, this is Z21 outer, and this is Z22 outer. Okay. So that's why we get Z11 is 80, Z12 again as 80, Z21 we get it to be 60, and Z22 we get it to be 140, and these are matching according to the answers provided in this sheet. Okay. So we will solve the next question. So this is a network which is provided, and this is a network one, okay, which is over here. The another network one similarly is over here. Same network. What we have to do is we have to determine the y parameters of this network, of the network one, and then there are two sets of network one connected in parallel with each other. Okay, and then we want to find the overall y parameters of the network. So what we will do first is we will determine the y parameters of network one alone. Then we will find the combined y parameters of two network ones connected in parallel. So let us start with finding out the y parameters of network one. So what we will write it down as this current is equal to V1 upon this 0.2 ohm resistor, and this is equal to V1 minus V2 upon 0.5. So when we apply KCL at node 1, we get I1 is equal to V1 upon 0.2 plus V1 minus V2 upon 0.5. So we can write it in better words as I1 is equal to 5 V1 plus 2 V1 minus 2 V2. So we get I1 is equal to 7 V1 minus 2 V2. This we will write it down as equation 1. Similarly, we apply KCL at node 2, and we get I2 is the current flowing in, V2 upon 0.25 is the current flowing out, and then V2 minus V1 upon 0.5. So we get I2 is equal to V2 upon 0.25 plus V2 minus V1 upon 0.5. This is equal to 4 into V2 plus 2 into V2 minus 2 into V1. So we get I2 to be equal to minus 2 V1 plus 6 V2. This is equation 2. So we write it in terms of matrices. We write equation 1 and 2 in terms of matrices, and we get I1, I2 is equal to 7 minus 2, 6, V1, V2, and this is A. Okay, this is A. So this is the, thus we have written in terms of how we write a Y parameter matrix. So this will be Y11, Y12, Y21, Y22. If you'll observe the matrix Y, these the first row, second column, the first row, second column, and second row, first column, they are equal. That is, Y12 is equal to Y21, which tells us that the network is reciprocal. Okay, so this is a reciprocal network. Thus, we have found it to be a reciprocal network. Now, so the first part of the question is we have to first, they have told us to determine the Y parameters of network 1. Y network 1 is Y11 network 1, Y12 network 1, Y21 network 1, Y22 network 1, which we have found. We have determined the Y matrix for network 1. Now, two-port network, network 2. This is two-port network, network 2. This is made using two identical copies of network 1 as shown above. Okay, there are two identical copies of network 1. Now we have to determine the Y parameters on network 2. Okay, now our goal is we have to determine the Y parameters of network 2. So we will proceed. Let us consider. So this is I1 prime and this is I1 double prime. This is I2 prime and this is I2 double prime. So we see V1 is the voltage applied to this network 1 and it's the same voltage which is applied to this network 1 also. So we get I1 is equal to I1 prime plus I1 double prime. I2 is equal to I2 prime plus I2 double prime. Now we know I1 prime and I2 prime is equal to Y11 of network 1, Y12 of network 1, Y21 of network 1, and Y22 of network 2 into V1 into V2. That we write it as I1 prime, I2 prime equal to 7 minus 2, 6 into V1 into V2. Similarly, we know since the networks are equal, I11 double prime, I2 double prime is equal to 7 minus 2, 6, V1 and V2. So we have in our analysis, which we have done, some studies which we did, we found that if the networks are in series, then we add the Z parameters matrix. If they are in cascade, then we multiply the ABCD matrices of T matrix of network 1 and T matrix of network 2. Now in parallel, and we will see what happens. Okay. Now we know that I1 and I2 can be written as I1 prime, I2 prime plus I1 double prime and I2 double prime. So we substitute these equations over here, this matrices, we will get I1, I2 is equal to 7 minus 2, 6, V1, V2 plus 7 minus 2 minus 2, 6 V1 V2. So we get I1 I2 is equal to 7 plus 7 minus 2 minus 2 minus 2 minus 2, 6 plus 6 V1 V2, or we get it as follows as I1 I2 is equal to 14 minus 4 minus 4 12 V1 V2. Okay, we get it as follows. So this is the effective Y parameters of network 2, which consists of two uh, parallelly connected networks of network 1. And we just found out that it is just you add the Y parameters of the both the networks and you get the effective Y parameters of the overall network, the equivalent Y parameters of the overall network. So when the networks are parallelly connected, it is best to represent the individual networks in terms of Y parameters. And then we add the Y parameters, Y matrices of those networks. And then we get the overall equivalent Y parameters for the network. Now, what if they are represented in terms of ABCD matrices, ABCD parameters? So we convert them in terms of Y parameters, then we find the overall equivalent Y parameters, and then we reconvert back into the ABCD parameters. So there are some certain formulas which are there, which are used to convert from Y parameters to ABCD parameters. Some certain relations are there, which you can refer to while solving these things. Okay, now we will go to the last and final sum of the assignment of previous year's questions. So we will just check the answers. Y11 network 1 is equal to 7. And this is in terms of mode. That is admittance. See, this is an admittance parameter. Okay, so you must remember, mentally, you must remember the dimension of this is in terms of mode, and terms of admittance. Okay. Similarly, we got this minus 2 minus 2. We got this to be 6. This is 7 into 2, so 14. Minus 2 into 2, so minus 4. Minus 2 into 2, so minus 4. 6 into 2, so it is 12. Okay. Now we will solve this sum. We will solve this sum and we will look into it. So this is the network which is provided to us. We are told to find the open circuit voltage gain. Open circuit voltage gain is V2 upon V1 when port 2 is open circuited. So that means I2 will be equal to 0. We should find the ratio between V2 and V1. Then they are telling us to find the short circuit current gain, which is AI, which is equal to minus I2 upon I1 with port 2 short circuited. So we short this port, so we will set V2 to be equal to 0. And then we will get the current gain is the ratio of I2 minus I2 upon I1. That is the short circuit current gain. Then they're considering a case when a 20 ohm resistance is connected across port 2, then the impedance seen from port 1 will be dash ohm. So we will connect a 20 ohm resistor over here. Then we will find the impedance seen from the port 1, that will be V1 upon I1. And we will get, what is the impedance seen by the port 1. Similarly, what we will do is we will connect a 20 ohm resistor across port 1. We connect a 20 ohm resistor across port 1, and then we will see the impedance seen at the input of port 2, that is V2 upon I2. Okay, so this is what we have to solve. So let us consider this network. We will put it in a new page so that we can analyze it well. So we will first we will apply KCL at the node 2. Okay, this is node 2, this is node 1. We will apply KCL at node 2. When we apply KCL at node 2, what do we get? We get I2 is flowing in plus 2I1, and V1 upon 10 is flowing out. That is V1 upon V2 upon 10 plus V2 minus V1 upon 10. So this is V2 minus V1 upon 10. So that means we get I2 plus 2I1 is equal to 2V2 minus V1 upon 10. Or we write it as 10I2 plus 20I1 is equal to 2V2 minus V1. This is equation A. Then we apply, this is when we apply KCL at node 2. Now we will apply KCL at node 1. What will we get? I1 is the current flowing in. I1 is equal to V1 upon 10 flowing out plus V1 minus V2 upon 10. So we get I1 is equal to V1 upon 10 plus V1 minus V2 upon 10. That is 2V1 minus V2 upon 10. So we get 10 into I1 is equal to 2V1 minus V2. This is equation B. Okay. So now we have applied KCL at both the input node and the output node. And we have gotten two equations. So now they have told us to find the open circuit current gain. We want to find the open circuit current gain. So A part is we want to find the open circuit current gain AV. For that, we will set I2 to be equal to 0. When we set I2 to be equal to 0, what do we get is equation 1 we get V1 minus 2V2. No, we get minus V1 plus 2V2 is equal to 20I1. It's equal to 20I1. This is equation 3. And we get, when we apply it in equation B, we get, but I2 is not there. So we have 2V1 minus V2 is equal to 10 into I1. Okay, this is 4. So we substitute 10I1 in here, over here, we get minus V1 plus 2V2 is equal to 2 into 10 I1, which is equal to 2 into 2V1 minus V2. So we get minus V1 plus 2V2 is equal to 4V1 minus 2V2. So we get 4 into V2 is equal to 5 into V1. So you want to find the open circuit voltage gain AB, which is equal to V2 upon V1, that is equal to 5 upon 4, that is equal to 1.25. Okay, so thus we have obtained the open circuit voltage gain, that is 1.25. Now, so what we have done, we have just written the equations of the node 1, node 2, and then based on our requirement, we have substituted that I2 is equal to 0. Now we want to find the short circuit current gain. So when we do short circuit current gain, we will short this V2, and so we will get V2 to be equal to 0. So next part is we want to get short circuit current gain. that is AI, that is equal to minus I2 upon I1. This is at a condition V2 is equal to 0. Now we apply this condition V2 equal to 0 to equation A and equation B. When we apply it to equation A, we get 10I2 plus 20I1 is equal to minus V1. Okay, 20I1 plus 10I2 is equal to minus V1. This is equation 5. Similarly, when we apply V2 equal to 0 to equation B, we get 10I1 is equal to 2V1. We get 10I1 is equal to 2V1. 10I1 is equal to 2V1. So we get V1 is equal to 5I1. So we substitute equation 6 in 5 and we get 20I1 plus 10I2 is equal to minus 5 into I1. So we get 25I1 plus 10I2 is equal to 0, or 10I2 is equal to minus 25I1. So we get I2 upon I1 is equal to minus 25 upon 10. So we get I2 upon I1 is equal to minus 2.5. Now we know the short circuit current gain IEI is equal to minus I2 upon I1. So that will be equal to 2.5. Okay. So thus we have found the short circuit current gain AI, which is equal to minus I2 upon I1, which is equal to 2.5. So now we will proceed with the third part of the question, where we want to find, you read it. Now we can connect a 20 ohm resistance is connected across port 2, then the impedance seen from port 1 will be dash ohm. So let us consider a case. Sorry. So what they're saying is we connect a 20 ohm resistor here. Okay, 20 ohm resistor here. So what do we know when we connect a 20 ohm resistor here? We get V2 will be equal to minus 20 into I2. We get V2 is equal to minus 20 into I2. So we will substitute this V2 is equal to minus 20 into I2 in the equations which we have derived earlier, equation A and B. So A is 10I2 plus 20I1 is equal to 2V2 minus V1. 10I2 plus 20I1 is equal to 2 into V2 minus V1. Okay. Now we put V2 is equal to minus 20 into I2. So 10I2 plus 20I1 is equal to minus 2 into minus 20 into I2 minus V1. So we get 10I2 plus 20 into I1 is equal to minus 40 into I2 minus V1. So we get 50 into I2 plus 20 into I1 is equal to minus V1. So this is equation 7. Let us assume this is equation 7. Now we know this equation B is 10I1 is equal to 2V1 minus V2. 10I1 is equal to 2V1 minus V2. 10I1 is equal to 2V1 minus V2. We know V2 is equal to minus 20 I2, so we write it down as 10 I1 is equal to 2 into V1 minus V2 is minus 20 into I2. So we write it down as 10 I1 is equal to 2 V1 plus 20 into I2. This is equation 8. So what do we do is, we substitute 7 in 8. We substitute equation 7 in equation 8 and we will get, let's just hold on a minute. We will get 10 into I1 is equal to 2 into minus 50 into I2. Okay. Plus 20 into I1. Okay, instead of substituting 7 in 8, what we will do is, we will write I2 in terms of I1 and V1. So I will write I2 in terms of I1 and V1. So first it becomes 5 into I1 is equal to V1 plus 10 into I2. So I2 is equal to 5 into I1 minus V1 upon 10. So this is equation 8. So I substitute equation 8 in equation 7 and we get 50 into I2 is 50 into 5I1 minus V1 upon 10 plus 20 into I1 is equal to minus V1. So I get 5 into 5I1 minus V1 plus 20 into I1 is equal to minus V1. So this 25I1 minus 5 into V1 plus 20 into I1 is equal to minus V1. So we get 45 into I1 is equal to 5V1 minus V1 is equal to 4V1. Therefore, we get 45 I1 is equal to 4 into V1, or V1 upon I1 is equal to 45 upon 4. That is equal to 11.25 ohm. Okay. And if you check, it comes out in the range we want. So V1 upon I1 is equal to 11.25 ohm. So that is the impedance seen from port 1 will be 11.25 ohm. When we connect a 20 ohm resistor across port 2. Now we will do the opposite. What we will do is we will connect 20 ohm resistor across port 1. Let us see. We will connect the 20 ohm resistor. Okay. So we know when we connect this 20 ohm resistor, we get V1 will be equal to minus 20 into I1. Okay, this is the value we get. So when we will substitute this v1 equal to minus 20 I1 in equations A and B. Now we know equation A is given as 10 I2 plus 20 I1 is equal to 2 V2 minus V1. That is 10 I2 plus 20 into I1 is equal to 2 into V2 minus V1. So we substitute the value of V1, we get 10 I2 plus 20 into I1 will be equal to 2 V2 minus or minus of 20 into I1. So we get 10 I2 plus 20 into I1 is equal to 2 into V2 plus 20 into I1. So these two get cancelled. We get 10 I2 is equal to 2 into V2, or we get V2 upon I2 is equal to 10 upon 2, which is equal to 5, is equal to 5 ohm. So in this case, we directly got it V2 upon I2. That is the driving point impedance seen from port 2 when we connect a 20 ohm resistor across port 1, we get it to be 5 ohm. We got it simply by just substituting this value in equation A. We got this result. And if we will check the result, we got V2 upon I2 is equal to 5 ohm, which is as desired by our, which is as per our requirements. So now let us do a brief recap of what we studied. So what we did was we first considered that there's a two-port network. This is the notation for the polarity of the voltages and currents. The current should flow into the network, but in case of ABCD parameters, the current I2 should flow outside. So that's why we either represent it in terms of a minus over here, or in case it is as already required I2 is in the opposite direction, then we proceed as further. So for ABCD parameters, we wrote the equations. So we first understood that the ABCD parameters can be in terms of Z parameters, Y parameters, ABCD parameters, or hybrid parameters. And then by considering ABCD parameters for a two-port network, we derive the conditions like when the network is symmetrical, when a network is reciprocal. So if the network is symmetrical, we found that the condition is A should be equal to D. Then when we consider that the network is reciprocal, the condition was AB minus CD should be equal to 1. AD minus BC should be equal to 1. That is the magnitude or the determinant of the T matrix for the ABCD parameters should be equal to 1. Okay. Then we consider the case where there's a combination of two-port networks. There are three combinations. It could be series connected, could be parallelly connected, could be cascaded, like one after the next. Now, there are other further complex cases where the input is series connected, the output is parallelly connected. The input is parallelly connected, the output is series connected, and so on. In this case, series connection to port networks, the input is connected in series and the output also is connected in series. So it becomes a simple case. So we have considered the simple case to just give you the broad understanding for a simple case so that when you come across complex networks, you're able to build on this and solve further. So we consider for series connection two-port networks, and we consider that the network are represented in terms of Z parameters. And when they are series connected, both input and output, then using Z parameters of the individual networks is very useful to find the equivalent parameters of the two-port network. So we found that when the network 1 and network 2 are connected in series, then the equivalent Z parameters is actually equal to the sum of the individual Z parameters, or the sum of the individual Z matrices for those two networks. Similarly, when we consider cascade connection of two-port network, that is when network 1 and network 2 is directly, like the output of network 1 is connected, is the input to the network 2. So when we find the overall parameters for the two-port network considering network 1 and network 2, we consider that they are characterized by the ABCD parameters of the individual networks, and the overall ABCD parameters is just the product of the two matrices. Okay, it's just the product. of the two individual ABCD matrices. Okay, those are the T parameters of the network. Then we consider an ideal transformer. How we represent that in terms of we have first told the various factors we have neglected, we have ignored. The losses, the leakage flux, the magnetizing loss, the magnetizing flux, etc. Magnetizing inductance, etc. We are ignoring. We just consider simple ideal transformer. And we represented that in terms of ABCD parameters. We also represent that in terms of H parameters. Then we consider a case when the two ideal transformers are connected in parallel. They are connected in parallel with each other, and we found the overall ABCD parameters for the two transformers when they are connected in parallel. Then we solved some four sums where the Z parameters is given on the network and some resistors and voltage sources are connected externally. Then what would be the overall Z parameters of the overall network, and that we obtain. Like this is in this scenario. We obtain that. Similarly, when the resistors connected at both the input and the output, what changes we observed, and we have solved that. Similarly, we consider the case when there's a network one. We first found the Y parameters of the network. Then that same network one is connected in parallel. The input is parallelly connected as well as the output is parallelly connected. So that is a duplicates, two identical network ones. They are connected in parallel, both in the input side and the output side. And then we found that the overall Y parameters is just the sum of the individual Y parameters. So that also we found. So this sum also was quite easy. And it will take some, just need to properly read the question and just solve step by step. And there's not any, sort of hidden, like something which is confused. It is just given step by step what you have to do. So that's why this was very easy. Similarly, for this question, we have to find a range of things like the open circuit impedance, the open circuit voltage gain, the short circuit current gain, what is the impedance seen from port 1, what is the impedance seen from port 2 under various conditions. So what we did was we just found out the overall equations, right? Not applying any assumption. We just found the overall equations for the two-port network in terms of I1, V1, I2, V2. We just found it. And we didn't find it in terms of any sort of parameter. We just found it in terms of I1, I2, V1, V2. For both, we did it by applying KCL at the output node and applied KCL at the input node. Then we have to find the open circuit voltage gain. This is not the current gain. This actually is the voltage gain. Open circuit voltage gain. So in that case, we open circuit this output port. That means I2 will be equal to 0. So we put the scenario that I2 equal to 0. We substitute that in equation A and B. And then we do the analysis and then we get the open circuit voltage gain. Similarly, for a short circuit current gain, we short the output port, that is V2 will be equal to 0. Then we further simplify the equations A and B and we get I2 upon I1. And the short circuit current gain is equal to minus I2 upon I1. So we get it in this form. Similarly, when we consider a 20 ohm resistor placed connected across port 2, in that case, we know that V2 will be equal to minus 20 into I2. We apply this condition and then we get the driving point impedance or the impedance seen from the port 1, V1 upon I1, that is 11.25 ohm. Similarly, we connect 20 ohm resistor at the input at the port 1 and then we find the overall impedance seen from the port 2 and we substitute that in equation A and B and we get a V2 upon I2 is equal to 10 by 2 is equal to 5 ohm. So thus we have solved the equations, solved the various sums as well as we have considered the necessary theory. So this would be very useful for you while you'll be attempting the exam for network analysis. So all the best. So we will end our session over here. Thank you.